So what we saw so far was some assumptions which were made about the movement of electrons and their structure and behavior within an atom, and how those assumptions changed as we shifted from the classical theory to the quantum theory. Now in these assumptions we came across this word called Fermi-Dirac statistics. So that Fermi-Dirac theory is what we're going to look at now. So first of all, the Fermi-Dirac distribution function is applicable to fermions, meaning particles which obey Pauli's exclusion principle. Now, what is the Pauli exclusion principle? There is a more technical definition which you might have come across in your 11th standard chemistry or elsewhere. But for the purposes of this course, I'll give you a very simple definition. Only two electrons can exist in an orbital, which is a particular energy level in a particular orientation. Only two electrons can exist and they have opposite spin. That is the Pauli exclusion principle. Now, for all particles which obey this principle, this Fermi-Dirac function holds true. And what is this function? F of E equals 1 by 1 plus e raised to e minus ef by kt, where capital E is the energy of the particle, EF is a reference energy level which we will be defining now, K is the Boltzmann constant, T is the temperature. And what is this F of E itself? It is the probability that a particular quantum state of energy E is occupied by an electron. Meaning, we saw that energy levels are quantized, meaning you have specific energy levels, right? So I have energy level A, B, C, D and so on. So F of A is the probability that the energy level A is occupied by an electron. So there are energy levels, some energy levels, so here each of these horizontal lines is an energy level and the first four lines are occupied by an electron, the lines above that are free. So for each line, F of that line is the probability that that energy level is occupied by an electron. That is what this function gives us. And it is given by 1 plus e raised to e minus ef by kt. So K is a constant, T is the temperature at which you are dealing with the electron, capital E is the energy of the electron. So those are either constants or they depend on the circumstances. But what is this EF? EF is a constant reference energy level called the Fermi level. So we are going to understand what that means now. So moving on, now we are going to understand what exactly this energy level EF is. So we'll take two cases, temperature equals 0 Kelvin and then temperature greater than 0 Kelvin, and we'll work out some mathematical conditions, and based on that we'll understand what this EF is. So we'll start with temperature equal to 0 Kelvin. And I'm going to assume my energy is greater than EF, meaning I'm talking about a particular energy level, right? And for that energy level, I want to find out what is the probability of its being occupied. So at temperature 0 Kelvin, I'll consider an energy level which is above EF, which has energy higher than EF. So 1 by 1 plus e raised to e minus ef by 0. The denominator is 0 because my temperature is 0. And anything divided by 0 is infinity. So this e to the power thing becomes e to the power infinity. So 1 by infinity is 0. So at 0 Kelvin, the probability of any energy level greater than EF being occupied is 0. Meaning if I say this yellow line is my Fermi level at 0 Kelvin, then no energy level above it can be occupied. All of them are definitely going to be empty as a rule at 0 Kelvin. So the highest, in other words you can say the highest occupied energy level at 0 Kelvin is my Fermi level. That is one possible definition. Now at 0 Kelvin we'll also see about the levels less than EF. 1 by 1 plus e minus ef by 0. Again here e less than ef, so this is going to tend to minus infinity because this is e less than ef, so this is a positive term and it's going to be a very small difference, so this tends to minus infinity. So this part becomes 0, and so 1 by 1 plus 0 is 1 by 1 is 1. So what it means is at 0 Kelvin the probability of occupation of any level lower than EF is 1. So okay, and we'll finish this also. And E equals EF, if you substitute that here, it becomes EF minus EF by 0, which is 0 by 0, which is indeterminate. So at 0 Kelvin, what exactly is this Fermi level? Fermi level is one of the energy levels, one of the multiple levels you have, such that at 0 Kelvin, it is not possible for any of the energy levels higher than it to be occupied at all. Probability of occupation is 0. And every level less than EF at 0 Kelvin is definitely occupied. Probability of occupation is 1. And EF itself, you cannot mathematically define whether it is occupied or not. Such a level is called the Fermi level at 0 Kelvin. Okay, so at 0 Kelvin, that is how we define the Fermi level. But it is not necessary that the temperature will always be 0 Kelvin, right? So let's say we apply some heat energy and some electrons get excited and they move higher. So now my temperature is greater than 0 Kelvin. Then what is my Fermi level? So now we will take E equals EF. So why are we taking E equals EF here, and we took all three cases, E less than EF, E greater than EF, E equal to EF there, is because there T equals 0 is the normal condition. 0 Kelvin is the room temperature, normal conditions. There we wanted to define what the Fermi level is in terms of the levels above it and the levels below it. So that is why we took three cases, and we understood that the levels above it cannot be occupied, the levels below it must be occupied. The Fermi level itself, it might be occupied or not, but we cannot mathematically define its probability of occupation. But here at a temperature greater than 0 Kelvin, we just want to know how the Fermi level is defined. So we only take E equals EF. So it becomes 1 by 1 plus EF minus EF by KT, which is 1 by 1 plus e to the power 0, 1 by 1 plus 1, which is 1 by 2. What does this mean? For all T greater than 0 Kelvin, the energy level at which probability of occupation is 0.5 or 1 by 2 is your Fermi level. So again, what are we talking about? So this Fermi Dirac function gives the probability of occupation of an electron, of an energy level by electrons, and the formula is 1 by 1 plus e raised to e minus ef by kt, where E represents the energy of that particular energy level, K is the Boltzmann constant, and T is the temperature. EF is the only ambiguous quantity. EF, we call it the Fermi level. It is also one of the energy levels. And how is it defined? It is defined differently for 0 Kelvin and for any other temperature. At 0 Kelvin, it is the highest possible energy level which can be occupied. Meaning anything above it cannot be occupied, anything below it must be occupied. And at any temperature except 0 Kelvin, any temperature greater than 0 Kelvin, EF is that level which has probability of occupation to be 0.5. So you take a particular level and the probability that this level is occupied by an electron is exactly 50%, then that is your Fermi level. So at T greater than 0, note that it does not say anything about the levels above or below. They could be occupied, could not be occupied. So it is not the highest occupied level anymore. It only says probability of this level being occupied is 50%. So that is your Fermi level.